Welcome to my presentation. My name is Jürgen Hackel and I'm currently a PhD student at the Infrastructure Management Group at ETH Zurich. Since I'm getting the opportunity to speak in front of so many mathematicians, physicists and engineers, and in the spirit of this old university, I thought it would be nice to make my presentation on the blackboard. Unfortunately, I don't have the time to do this live, so I drew already my presentation at home and brought it in a digital form with me. I know this is a little bit untraditional, but I hope you still enjoy it. Today I'd like to talk about Markov marked point processes and how they can be used to create multi-layer spatially embedded vertices. The outline of my talk is the following. First of all, I'd like to start with the reason I am doing this kind of research as a civil engineer. Then I'll give a brief explanation what are Markov point processes and how they can be extended to marked processes. After this, I'd like to draw a connection to multi-layer spatially embedded random networks. And finally, I'd like to show you a possible application of this approach. As a civil engineer, my focus is on infrastructure networks, and therefore I'll use road networks as an example throughout these presentations to explain my ideas and methods. However, the methodology should be applicable to all kinds of networks. Illustrated here is a small part of the Swiss road network. When we model such a network as a graph, we can approximate the roads as edges and the intersections as vertices. The focus of this talk is on the vertices and finding appropriate models which describe this type of pattern. Road network contains several layers of hierarchies, for instance, motorways, primary roads, secondary roads. Each intersection can be classified in a similar manner. How this classification is done, I will explain later in my talk. For now, let us focus on only one set of vertices, the red dots here, which represent motorway intersection. Contrary to classical point processes, I'd like to define these vertices conditional on each other. Or in other words, each location of the points depends also on the location of all other points in the set. In order to formalize this idea, let's go back to the classical Poisson point process, which is completely specified by its intensity function lambda. There is a clear meaning to this parameter, and different models can be formulated easily based on this. However, for Markov point processes, this intensity function is not convenient nor a useful modeling tool because the intensity of such a process depends on several competing effects. In order to describe this process, we use the related concept of conditional intensity. Heuristically, this term can be interpreted as the conditional probability of finding a point of the point process x inside an infinitesimal region around the point u of area du, given the position of all other points around this region, where lambda is now the conditional intensity and behaves like the normal intensity, except that it depends on the rest of the pattern. Coming back to our road example, imagine each intersection needs a physical space of radius r. No other intersection can be built within a distance r of any other existing point. Therefore, it makes sense to assume that the conditional intensity lambda is equal to 0 for any location u inside of radius r of an existing point x, and lambda is some arbitrary value otherwise. This is a so-called hardcore process, to which I will come back later. Omitting many technical conditions and steps, the conditional intensity at location u for a point pattern x with probability density f of x can be expressed by this fraction. Leaving out all technical derivations, suitable probability density functions can be derived by this theorem. Here, the probability density f of x is proportional to the unnormalized density h of x. which is a product of different interaction functions phi. To get f of x, a normalization constant has to be derived, which might not always be easy. However, the conditional intensity does not depend on this constant. Now we can generate our general model. Since we're interested in interactions between different points, we can create a pairwise interaction process, taking only the first two products. One well-known and simple process is the so-called Strauss process, where phi1 is beta and phi2 is gamma if the point lies within radius r and 1 otherwise. This is the conditional density for this expression, where t is the number of points of x that lie within the distance r of the location u. The nice properties of these models are: first, if we have a gamma which is equal to 1, we have a Poisson point process with intensity beta and therefore complete spatial randomness. Second, if gamma is 0, we end up with a hardcore process where no point can lie closer than radius r. Unfortunately, this process is not defined for gamma greater than 1. So in order to account also for this, we have to use other point processes. For instance, the Gauss saturation process. It is a little bit more complicated than the Strauss process, but it also defines gamma values greater than 1, which accounts for clustering of the points. Okay, now let's make it a little bit more interesting by adding marks to the point process. Our point process is now not only defined in A, but also in the space L of possible marks. A marked point pattern drawn from Y is now an unordered set of tuples containing the location of the vertex and also the assigned layer. All the previous assumptions and properties hold, we only have to extend our equations. An important difference now is that the interaction functions phi depend additionally on the layer in L. However, assigning layers to vertices is not trivial. In general, 3 different ways can be formulated. The independent model is the simplest. Here, the position of the layers and the vertices are assigned conditional independent. The second way is conditional on location, where the locations are determined in advance and based on the locations the layers are assigned. For example, in the road network, we have vertices which are further apart of each other, and therefore it's more likely that these vertices will be assigned to the layer motorway, for instance. And the third way is conditional on marks, where the first layers are assigned and afterwards are placed at a certain location in A. This might be the case for 2 different infrastructure networks. Now, let's apply the methodology to a real-world example. Here you see parts of the Swiss road network, including motorways, primary and secondary roads. The graph contains around 5,500 vertices and 8,300 edges. To model the real-world network, an inhomogeneous Strauss process is used, where a spatial field Z is added. In this case, the population density is used as a spatial field with the assumption that it's more likely to have more intersections in denser populated areas. Here is one realization of the model. We can see there are some similarities to the real world, like more vertices are in the northern part of Switzerland. But in order to get more insights to the model, we can run thousands of these simulations and analyze different network properties and measures. Okay, in order to fit our model and the parameters used, beta, gamma and r, we minimize the least square error for the diameter, average shortest path length, clustering coefficient and degree associativity. The observed measures are shown here in blue. What we can see is that there is a quite nice match considering only the few parameters used for our models, but we have some underestimations of the edges and the vertices, which is caused in this case by the fact that a single layer network cannot account for different types of roads. Considering multiple layers allows us to get better results. Here, for instance, we see these two networks compared against each other. On the left-hand side, the single layer network, and on the right-hand side, the multi-layer network, which is closer to the real-world network. And here is one realization of such a multi-layer network. In the first layer, in red, we have the motorways and primary road vertices. In the yellow layer, we have the secondary road intersections, and when we collapse these two layers, we reach the green layer, so that the total network considered. To conclude, I presented today a very simple method to create multi-layer spatially embedded vertices using Markov marked point processes, which allow to approximate a real-world network quite good, considering that only a small amount of parameters are needed. What I completely omitted in this talk was how the edges in the multi-layer spatially embedded random network were created, and this will be topic of another upcoming presentation in Barcelona. Thank you very much for your attention.